Hello everybody. I was going through my academia profile, the countries tab. Here they generally provide the global map and they highlight the countries where the papers uploaded are being read. So this is, I think, 60 days report. Yes, this one is 60 days report. So if I sort it from low to high or high to low, then United States ranks number one. Second comes India. Third comes Germany. Germany, of course, should come should get at least one position in the top four. So it is there naturally because my work is related to Riemann hypothesis, and Bernhard Riemann was from German. So um, good to see that my papers are being read all across the globe. But uh, I have noticed one thing. My last paper, where the total work was compiled, that paper is not being read by many people because all the videos I posted might had got the old papers link, and I didn't change them manually all the links one by one. Maybe that was the reason. My old papers are being read. So I request all of you to read this paper because here I have done a lot of uh, corrections and updations, you can say, based on the YouTube comments I got, and also a lot of feedbacks um, from my audiences. So I should recommend you to go through this particular paper where my title is remaining same everywhere. It is the same title I have been using, but just see the numbers all are in proper case, and 3 is in the numeric form. Please go through this paper, and or if you can download, that will be best. Although the 408 minutes count is good, but the 188 views is annoying me. Please, I will ask to everybody to go through this paper because this is the most updated one. Okay, let's open this paper. I have downloaded it. I have downloaded it, and let's open this paper, and I will take you through my paper once again so that you can see whatever latest changes I have done. Have you gone through or have you gone through it or not? You can check it. So the initial part is the introduction part, so all mine know. So what I will do here, I'll go each page by one or 2 seconds, and I'll see whether this is the updated one, and I'll put a tick mark so that mm, you can take it as a confirmation that this is the video you are referring and the same paper you are referring. Because of the views, I have not deleted my old papers because lots of people has already shared the links, so I don't want to break those links. Okay. So as you may know, Euler's induction approach, that was the first the first mathematical work on zeta function. These are standard things you might know. Then Euler derived the summed product form of the zeta function. Here he applied some geometric series and sieving techniques. Then he came out with the infinite product form of primes, and he verified it through geometric series summation formula also. All this he was doing while solving the Basel problem, and famously after that he got recognition, but he had to struggle a lot for that. So this detailed derivation of zeta 2, which came to be pi square over 6. Yeah, this Basel problem. Bernoulli's numbers plays a crucial role here. So these are very standard things. You might get it anywhere in the internet. I'm not going into details of this. Yeah, Euler faced a lot of criticism for this work also. Initially he had to face a lot of criticism, but eventually it convinced the mathematical community. Then come the value of zeta 3. Euler's work was centered around the zeta values for even numbers, but he was clueless on the odd numbers. Here Ramanujan's gave a try. Also, um, Apres constant, which is zeta 3, is being he has got a Ramanujan gave some series representation, but still today we don't have any good formulation for even odd numbers. In 1979, Roger Apre proved that zeta 3 is irrational. This was a landmark result in number theory, and he showed that zeta 3 cannot be expressed as a rational of two integers. Apre's proof involved mathematical advanced techniques in number theory. Then come Ramanujan's contributions. He then gave this representation which converges rapidly. Zeta 3 appears in various fields like mathematical physics. Now let's enter the Riemann's work on the zeta function. Riemann zeta function. It's just an extended domain of Euler's original zeta function, but still we call it Riemann's zeta function because Riemann expanded the function to whole of the complex plane. Euler's work was restricted to only even numbers greater than 2, greater than 1. For as I told you that for even for odd numbers he didn't have a good formulation, but he could generalize the even number valuations. So it is a very restricted domain. But Riemann um, extended this domain to the whole of the complex plane. Explain except one pole that is considered to be the simple pole of zeta functions, which uh, which is s is equal to 1. Riemann's work was based on Dirichlet's eta function and many others pioneers' work. The marvel of genius of Riemann was the derivation of the functional equation, which looks like this. Zeta of s is equal to 2 to the power s pi to the power s minus 1 of sine pi s over 2 gamma of 1 minus s and zeta of 1 minus s. Here we can see the analytical reflection, also the periodicity. Almost all aspects of zeta functions are covered in this functional equation. So these are the derivation of this form, the functional equation, Mellin transformation of the theta function, then splitting the integral. These are also all standard stuff available over the net. You can refer it. And completing the functional equation. Reflection property. So here comes the Riemann hypothesis. After analytical continuation of the zeta function to whole of complex plane, so Riemann saw that Riemann particularly was interested in to locate the primes, because we have seen the product form deals with the primes. So he wanted to see the heights of these functions, so that he can get an idea about the prime density up to a given number. For that he was testing, and he saw initial few values are lying on the critical line called real part of s equals to half. So he hypothesized that, based on that, he hypothesized that all other primes should follow the same pattern. So this became the Riemann hypothesis, which is till today it's unproven. More than 150 years has passed since Riemann hypothesized, but we don't have any clue yet. And based on this Riemann hypothesis and Riemann's work, a lot of other theorems has been proven, like the prime number theorem, which gives the which originally originally formulated by Gauss, little boy Gauss. Then this has been proved by, I think, two famous mathematicians, De La Poussey, and I have not mentioned. Maybe I have mentioned somewhere. So pi of x. This is the prime counting function. Pi of x. Riemann derived an explicit formula based on this, which involved the logarithmic integral of x, Li of x. and there is a bound. So if his hypothesis is true, then we get a very narrow bound of the pi of x, so that we can estimate the number of primes more precisely, because the error term is gets, as the number grows, the error term uh, gets smaller, very smaller. Hadamard and Lavelle-Poussey. These guys proved the prime number theorem. These two guys. Okay, now let us move to an attempt to prove his theorem, his hypothesis. Before that, we will brush up some basic things and work upon some more extensions of zeta and related functions. Then we'll jump to the proof. My approach. In my approach, I explore a novel approach to understanding and potentially proving the Riemann hypothesis. Rather than relying solely on traditional methods in complex analysis, I focus on the logarithm properties and symmetries inherent in the problem. So whole approach centers around the logarithmic aspects of zeta function. Here I am telling I begin by redefining the imaginary unit I in terms of logarithms, specifically I equals to ln2. This may sound little arbitrary, but believe me, before I arrived this conclusion, I had to do a lot of maths and a lot of cross checks, double checks. Then see that this is the only way. All the way converges to this particular thing of I equals to being ln2. Then only my uh, whole work sits well with the Riemann's original hypothesis. Now, why it should work and why it shouldn't, that's a matter of questions and debates. But uh, I have placed my logics before I jump to this conclusion. I have tested some of the intricacies and implications, and I saw a lot of potential in this. So that's why I took this particular path. Devising the strategy. So as I told you, it will be log related, but there are other functions involved in the functional equation. So factorial functions and the zeta functions. So yeah, there are a lot of symmetries involved in this. So we have to work on that also. Let's start with the functions we need to work one by one. Let's start with the pi function first. So it is also a product of the great Euler. So pi function has got a factorial representation, which has got a recurrence relation, like uh, it it can recur the relationship of needed for factorials automatically through this integral form. But that was not enough. Also, pi function has got its own pole. Its poles occur at all negative integers, like s is equal to -1, -2, -3. So Euler have seen this, but later in his career, he thought to move to gamma function, which is another form of another recurring relationship carrying the factorial properties. But the argument is a little different here. Here it is inside the integration. You can see the parameter t has got a exponent of t to the power s minus 1, whereas in case of pi it was pi function, the factorial phi function, capital pi I'm talking about. It was only s. So this shift gave him the opportunity to explore little deeper, and magically he could remove some of the poles of the pi functions. Now you can see for s is equal to minus n, where n is a non-negative integer. Yeah, but pi 0 was not defined. Gamma is 0 is defined here. Non-negative integers means gamma of 0 is defined. So at least he could remove one pole. So my idea is to work the same coastal line, work along the same coastal line and dig something deeper. If we get something meaningful, we will be using that. Similar to capital pi and gamma, I introduced delta function. Delta function is just the same integral form, but the parameter t has got an exponent of s minus 2. That means I have shifted down the parameter, the power exponent, by one more unit, and the same recurrence relation and everything follows. So here the poles will be